Welcome to The Explainer, where today we're tackling a really fascinating puzzle in AI. Why making an AI think longer and harder doesn't always make it smarter. In fact, it turns out that just like us, they can actually think too much. So, let's just jump right in with a question that feels a little counterintuitive. We're always trying to make AI more powerful, right? To get it to reason more deeply. But is it really possible that more reasoning could lead to worse results? Well, it turns out the answer is a big fat yes. You see, researchers have actually spotted this really weird overthinking problem. It suggests there's an optimal length for an AI's chain of thought, and if it goes past that point, its accuracy actually starts to drop. This is a huge head scratcher, and it's left a big theoretical gap in how we understand AI reasoning. So, to get to the bottom of this, we've got to look at how we've traditionally tried to analyze AI thought. And honestly, the old way of doing things, it's like trying to appreciate a masterpiece painting by looking at it one pixel at a time. You just completely miss the bigger picture. Yeah, that old framework is totally stuck at the token level, just focused on the tactical job of picking the next word. But the real magic, the actual reasoning, that happens at a much higher strategic level. It's all about the core ideas, the grand plan for solving the problem. And the sheer scale of this problem, it's just mind-boggling. At the token level, the number of possible word combinations just explodes exponentially. I mean, trying to build a theory based on this is like trying to map the entire galaxy by visiting every single star one by one. It's just not going to work. All right, so let's shift gears and talk about a new framework that offers a completely brilliant change in perspective. It's called Coet space theory. And what it does is it zooms way out from those individual stars to see the whole semantic galaxy at once. So instead of getting bogged down in this ocean of individual words, Coet space is smart. It gets that tons of different sentences can basically mean the same thing. So it clumps all those similar thoughts together and treats the whole reasoning process more like a smooth journey through this continuous landscape of meaning. And this completely reframes the entire process. Think about it like this. AI reasoning isn't just about picking the next word anymore. It's a search for the best answer. It's like a hiker trying to find the lowest point in a valley. Every thought is another step down the mountain, and the AI is constantly tweaking its path, trying to get closer and closer to the bottom, which is, the right answer. Okay, so with this new way of looking at things, something really fundamental becomes clear. It turns out finding the best answer isn't about thinking forever. It's this delicate balancing act, something that's super familiar to anyone who's worked in machine learning. So what we're really looking at are two opposite risks. On one side, you've got thinking too little. Researchers call this underfitting. And on the other side, you have thinking too much, which leads to overfitting. Let's dig into what that actually means. Right, so when an AI's chain of thought is way too short, it's kind of like trying to solve a super complex physics problem with just elementary school math. It's just not equipped for the job. It literally doesn't have the thinking space to work through the steps it needs, so it ends up failing even on problems it's already seen. In machine learning terms, that's a classic high bias situation. But then you have the flip side. If that chain of thought gets too long, the model suddenly has way too much capacity. And what happens? It starts memorizing all the little oddities and noise from its training data, instead of learning the actual general rules. So the moment you give it a new problem it hasn't seen before, it completely falls apart. That's your high variance problem right there. So what's the crucial takeaway here? This is the classic bias-variance trade-off we all know from machine learning, but now we're seeing it applied directly to the reasoning process itself. And the theory predicts that if you were to plot the AI's error rate against how long its thought process is, you'd get this really clear, distinct U-shaped curve. And that U-shape is everything. It tells us there has to be a sweet spot, an optimal length of thought that is just long enough to solve the problem, but short enough to avoid overfitting and memorizing all that junk. It's that perfect Goldilocks zone for AI reasoning. Not too short, not too long, but just right. Okay, this is a beautiful theory, right? But does it actually hold up in the real world? Well, it turns out a whole bunch of experiments give it some really strong validation, and they show us exactly how we can start putting these ideas into practice. So, the research pinpoints four key factors that really influence this optimal thinking length. We're talking about the task's difficulty, the model's own capacity, the learning algorithm being used, and optimization noise. And this is huge because it gives us a practical roadmap for building AI that's not just bigger, but actually smarter and more efficient. First up is task difficulty. And this one's pretty intuitive, right? The harder the problem, the more thinking it's going to take to solve it. The data clearly shows that for a really tough math problem, the AI settles on a much longer chain of thought than for an easier one. Basically, it needs a longer runway to get off the ground when the problem is more complex. Okay, now this next one is really fascinating. What about the power of the model itself? The data actually shows that bigger, more powerful models learn to use shorter and more concise reasoning paths. That feels backward, right? Well, it's because those big models are way more likely to overfit. So they almost instinctively shorten their thinking to stay focused on the general principles, not the noisy details. So the really big takeaway here is that there's no magic number. There's no single best length for an AI's thought process. It's all a dynamic balancing act. The perfect amount of thinking is always going to depend on this delicate dance between the difficulty of the task and the power of the model trying to solve it. So you have these four key factors, right? Task difficulty, model capacity, the learning algorithm, and noise. By understanding these levers, we can finally get past this brute force approach of just throwing more computing power at a problem. We can start making them genuinely smarter. At the end of the day, what this COTE space framework gives us is a really solid theoretical foundation. It finally helps explain that weird overthinking problem. And, more importantly, it gives us a guide for building the next generation of AI agents, ones that can reason effectively without, getting lost in their own thoughts. And all of this leaves us with one final, really provocative question. I mean, think about it. We've gone from just asking an AI to think, to now having a way to understand the very structure of its thinking. So now that we can actually measure it, the real challenge begins. How are we going to guide it?